In this word problem, it says here the aorta has an inside diameter of approximately 0.5 centimeters, compared to that of a capillary. And the size of a capillary is 10 microns, and that is only here for comparison purposes. In addition, the average speed of blood flow is approximately 1 meter per second in the aorta. If there is a blockage of about 75% of the original diameter, the question is asking us what is the velocity in meters per second here at the blockage. Well, looking at the word problem, let's change this to millimeters. Only reason for that is to just work with whole numbers. So let's change this over to millimeters, 0.5. You don't have to do this. You can go straight to meters. But for this video, I'm going to change it to millimeters. Multiply by that 10 millimeters on top and 1 centimeter in denominator, so they cancel out. 10 times 5, 5. So the diameter of the aorta here at this point is 5 millimeters. And we'll call this 0.1. And at the restriction right here, we'll call that 0.2. Therefore, the diameter of 1, D1, is equal to 5 millimeters. And I only did that so I can work with whole numbers. And it says here, if there's a blockage restricting the diameter, the 5 millimeters, to 75% of the original diameter, that will be D2 here. Diameter of 2. We don't know what that is yet because we got to do the small calculation. I'm going to redraw this over here. So here is the aorta. And it has a constant diameter, and then it starts to get reduced because of the blockage to a smaller diameter here. And if you recall at a prior video, this would be no different than the water hose. We have the water hose here with a specific volume flow rate, and then you put your thumb at the end of the water hose restricting the exit, making it smaller. This is the same scenario. And the equation we're going to use for this, let's have a look at our equations, is continuity. The equation of continuity is this one. And later on, we're going to look at the volume flow rates. But this is the equation we're interested in. And the volume flow rates, this simply means the volume of blood going in must equal the volume of blood going out. Let's do that. So we have here, let's see, the diameter across here we know, D1. Notice it's 5 millimeters. The diameter across here we don't know yet. But we can look at the volume flow rate, Q1, is equal to area 1, velocity at 1 here. Let's call this 1. And we'll say that the blood is flowing in that direction. So the volume flow rate here must equal the volume flow rate that exits at this point. Equal to the area 2, velocity of 2. Combining these two together, because what goes in must come out. And if it doesn't come out here at the same volume, then this blood vessel right here will start to expand and blow up. Okay. So we want Q1 must equal Q2. Equation of continuity. We're equating the two right-hand sides together. And we have, we'll go with this one first. The cross-sectional area times the velocity entering here, that this is the blood, has to equal the cross-sectional area exit and the velocity of the blood exiting. We want to find this one here, V2. So let's calculate what D2 is. It says here that if there is a blockage restricting the diameter to 75% of the original diameter. Okay, let's look at that. D2 is equal to 75% of the original diameter. That usually means multiply. So 75%. 75% is the same as 75 divided by 100, and that's equal to 0.75. times the original diameter, 5 millimeters. And I changed it to millimeters so we can work with whole numbers. 0.75 times 5 millimeters. That's equal to 3.75 millimeters. But it's a 75% blockage, and this is 3.75 millimeter hole of the diameter of the hole, or is that correct? Let's look at this a little closer. Here is the original. We'll just draw a circle here. The diameter of this is 5 millimeters. And this diameter, 3.75 millimeters, would be somewhere about here, about 3.75 millimeters. That will be at the diameter 3.75 millimeters. That's 75% blockage. That doesn't quite look right. Let's consider a 50% blockage. Consider 50% of 5 millimeters. 50% of 5 millimeters is equal to 2.5 millimeters. So a 50% blockage ought to give me an opening in the center of 2.5 millimeters. If this is 3.75, 2.5 will be somewhere in here, half of it. So this will be a diameter of 2.5 millimeters at a 50% blockage. And at 75% blockage, we're saying that the diameter should be 3.75. Well, that doesn't quite look right. So what we really need to do is make a subtraction. This is the actual blockage. The 3.75 millimeters is the actual blockage. And what's left over is the opening that we are interested in. So this does not equal. So we'll need to make a subtraction. If this is the actual blockage, here's the actual blockage. If we take the original diameter minus the actual blockage, to give us the opening that's left over. Something like this. We'll take the original diameter and subtract from it the blockage of 75%. That is equal to 1.25 millimeters. So what we calculated first, 75% of 5 millimeters, this is the amount that is blocked. How much is blocked? Now, so if we could take a diameter, go down somewhere around here. So this much is blocked. And we subtract from what's blocked from the original 5 will give us what's open. That's what this is. So 1.25 millimeters is in fact the size of the opening here. This is how much is open. This may better be described using areas. So 75% of this area is blocked. So that would be all of this area here is blocked. And the area left over will be this portion. But I'm trying to stay here with diameters, working with the diameter. So it's, in order to calculate D2, it's the original 5 millimeters minus the portion that is blocked, giving us an opening of 1.25 millimeters. That's D2 up here. That little opening that's left over, or the opening in here, would be 1.25 millimeters. And let's make a list of what is given. We know D1, diameter 1 is equal to 5 millimeters. But in our equation, the continuity, we need to know the areas. And that's a circle. And the area of a circle is pi r squared. And we need to know A1 is equal to pi r squared. But there's another equation that can be used for areas of a circle, and that is pi times the diameter squared divided by 4. These two are the same. This one uses diameter, this one uses the radius. Since we're given diameters, I'm going to use this one. Putting in the numbers then for area 1, pi times the diameter that's given to me is 5 millimeters. But I need to change that to meters because in the end I need to go to meters per second. And the velocity is also given to us in meters per second, so I need to change to meters. So let's change 5 millimeters to meters. Let's see now. You need millimeters in the denominator and 1 meter in the numerator. And let's be 1,000. Follow the units. Millimeters gives us that. So divide by 1,000. That equals to 0.005 meters. Back to our equation. The diameter squared, 0.005 squared. Everything divided by 4. And the units will be meters squared. So that would be the cross-sectional area of 1 here. Or right here at the opening. The large portion of the aorta. Do the same thing for the restriction right here. Now that we know what the actual opening is. Diameter of 2. D2 is equal to, we said it was 1.25 millimeters. And we're going to change that to meters. Follow those units. So that's in the numerator. This is in the denominator. I want meters in the numerator. And there is 1,000 millimeters to 1 meter. So follow the units and the numbers go for the ride. Dividing this by 1,000. 0.0125 meters. Finding the area, A2. This is at the restriction. Is equal to, I'm going to use the diameters again, pi d squared divided by 4. That's equal to pi times diameter, 0.00125 squared. Everything divided by 4. Now you can put this in your calculator and come up with a number, 0.000, whatever it might be. I'm going to leave it in this form. And the unit is meter squared. Also, we know here at the entrance, right there, the velocity is given to us as 1 meter per second. So the speed of the blood entering the aorta, just prior to the blockage, is equal to 1 meter per second. Again, I'm with our list of given. And we want to find the velocity 2. What is the velocity here at the restriction? And I'll just draw an arrow of the blood flowing out. So blood flows in this way. It has a velocity v1. And it exits here at a velocity v2 with this restriction. And we're only interested right here at this portion. Here's our equation of continuity. So we now calculated the areas. We know what the velocities are. It's a matter of putting the numbers that we have into that equation. Matter of putting all of this, A1, A2, V1, V2 into our equation. And solving for V2. I'm just going to turn the page and do just that. And, keep this handy. So equation of continuity, cross-sectional area times the initial velocity, or entering that area, is equal to area 2 and velocity 2. So this would be 0.1 and 0.2. So what goes in must come out. Which I should say the volume flow rate going in should equal the volume flow rate exiting. Putting in the numbers now for area 1. Area 1 we calculated as this term without actually doing the calculations in the calculator. So I'm going to use this term for area 1. Everything divided by 4. That's area 1. Multiplied by the velocity, or that'll be meter squared. Multiplied by the velocity, 1 meter per second. And that is equal to area 2. And area 2, calculated earlier, as this. Putting it in the raw form, pi times 0.00125, everything squared, all of that divided by 4, times velocity 2. Rearranging in order to solve for velocity. This is a number, like the number 10, or the number 5, or number 22. It's just a number. If I were to put this in a calculator, it'll come up with some value, 0.000 something or other. In this form, so that's the number. I'm going to divide both sides by this entire number in order to move it to the left-hand side and isolating V2. And it looks like this. You have the numerator here, pi times 0.005 squared. Everything divided by 4, multiplied by 1, or meters squared, meters per second, multiplied by the initial velocity. Everything here divided by, take that whole term and bring it to the denominator. Everything divided by 4, and what's left over is velocity 2. In this form, what we have here is a fraction divided by a fraction. It's like 1/4 divided by 1/4, or I shouldn't say a quarter because it's a different value, but 1/4 divided by 1/8. So it's a fraction divided by a fraction. And if you rearrange this accordingly, you will see that the 2 pi's will cancel out, and the 2 number 4's will cancel out. And this is just 1 meter per second. So number 1, if 1 times anything will stay the same. Let's reduce this to 0.005 squared times 1, and the unit will be meters per second, because meter squared, this one is also meter squared. Meter squared cancel out, giving us only meters per second, divided by, what's in the denominator, 0.00125 squared. And the units will be meters squared. Velocity 2 then reduces to this simple form. Putting this in our calculator. And I have 0.005 all squared divided by 0.0012 all squared is equal to should be 125, and do that again. 0.005 squared divided by 0.00125 squared equals, there we go, that's 16. And the unit is meters per second. Therefore, and it's already in 2 significant figures. Everything here given to us originally was 2 sig figs. 1, 2, 1, 2. And this is a nice even number at 2 significant figures in meters per second. Therefore, velocity through the restriction is 16 meters per second. Wow, that seems pretty high in terms of meters per second. So 1 meter per second enters here, and 16 meters per second at that restriction. And the smaller that restriction gets, the greater that speed will become. But is this correct? Well, we can do a quick check. Do a check. We know that the volume flow rate in must equal the volume flow rate out. Volume flow rate in must equal volume flow rate out. So we can calculate volume flow rate in. U1 is equal to A1 B1. And we're back here. So all of this is part of continuity. These 2 equations, they must equal each other. Q1 must equal Q2, and which in turn gives us the equation of continuity. So we're going to do this separately now. So let's find out what the volume flow rate is in and the volume flow rate out. Now that we have the areas and the velocities, we can calculate these 2 separately. So volume flow rate in here is equal to And using the areas that I had earlier, area flow rate 1, pi times 0.005 squared, everything divided by 4, that's the cross-sectional area going in. Here's the restriction, that's this one here. Multiply that times velocity 1 was 1 meter per second, meter squared. Putting all of this in our calculator, the answer is 0.0009635, and the unit is cubic meters per second, volume flow rate. Let's do that now for Q2, exiting. A2, velocity 2. A2 we had earlier, be this area. It's pi times 0.00125 squared, everything divided by 4, meter squared, times the velocity, which we calculated to be 16. Is equal to. Let's put that in our calculator. And we have second function pi times 0.00125, everything squared, equals. Divide that by 4, equals. And let's multiply that by 16. And there's that equal sign. And that number is the same as the number we had earlier, 0.000019635, and the units, meters times meter squared. So the volume flow rate in is equal to the volume flow rate out. What's different is this guy, all because of this plaque buildup here, restricting that area.